Hey, all you calc heads, we are back and we are talking about derivatives of a couple trig expressions today, derivative of sine and cosine. And you can prove it with limits, which is pretty cool on its own. It uses sum and difference identities. But I like this. It's not exactly a proof, but kind of an idea. So to do this, I'm going to look at the graph of y equals sine of x. Basic graph sine of x, the period is 2 pi. The amplitude is 1, -1, midline, y equals 0. Okay, so I'm going to look at the slope at different spots, since that's what the derivative gives you, right? So the slope right here at 0, it's certainly something positive. If I were to try to estimate and get these out. Now it's difficult because the scale is in terms of pi. That's a half pi, so that's like 1.57 approximately. But this right here, if you'll just take my word for it, it's you can think that 1 would be approximately right here on the x-axis, and that point looks like it's aiming right about there. That slope is perfectly 1. At x equals 0, the slope is 1. And so that means that on the derivative graph, when x is 0, when you plug in 0 to the derivative, you get out 1, because that would represent this slope right here. So what I'm going to do is, that means the output, or the y-coordinate of the derivative graph, would be 1 at x equals 0. At pi over 2, or 0.5 pi, this is right where we've hit the maximum, so our slope is 0, right? And so that means at pi over 2 on the derivative graph, my y-coordinate, or the output, should be 0, right? The y-coordinate on the derivative graph represents those slopes on the original. That's a big idea, and a little confusing at times, but this is a good idea to start to see this. At pi, it's definitely negative, hopefully you see, and it's actually, since it's the same symmetry as this, just negative, that slope is -1, perfectly -1. So at pi, y prime is equal to -1. So you get a point here, and you might start to see something shaping up. At 3 pi over 2, or 1.5 pi, we're here at the minimum, so you get a slope of 0 again. So we're back to having a y-coordinate of 0 here. And then at 2 pi, it's the start of a new cycle. You get your slope of 1 again, so we are back to having a y-coordinate of 1. And you've got it. Maybe you can even see it right before I did that. Hey, what shape is that? That is cosine of x. So the derivative of sine is cosine. Pretty cool, right? And if you wanted to think about the slope of cosine, or the derivative of cosine, you could kind of do the same thing and just say, well, now that I've got the cosine graph, let me just think about its slope. And it wouldn't take that long. Okay, at that point, the slope is 0. I'll just do a super quick sketch over here. And so the y-coordinate would be 0. Right here, the slope would be -1. So we'd have a y-coordinate of -1. Right here, the slope is 0 again. So we're back to being 0. The slope here is +1. So we're here having a y-coordinate of +1, and then here we're back to having a slope of 0. So you'd get this. Now what kind of shape is that? It's not sine, it's negative sine, right? Because it starts with a trough and ends with the crest. So the derivative of sine is cosine. The derivative of cosine is negative sine. So there's two rules really in one, and that's pretty cool, I think. So here's that Leibniz notation used as an operation. Derivative of sine of x with respect to x is cosine of x. The derivative of cosine of x with respect to x is negative sine of x. Okay, those are the two rules for now. And those are the building blocks. You want to know the rules of tangent, secant, cosecant, all those good ones. It all starts with these two. So let's deal with these two today. Now, frequently it would not just be normal sine, cosine. There might be coefficients and other terms and things. So find the derivative of each function. If y equals this, then the derivative y prime, being that good habits, good notation, is, hey, that coefficient just comes right along for the ride. It's negative 2/3 times the derivative of sine. The derivative of sine is cosine. So our answer is negative 2/3 cosine of x. Easy, right? Now, if that coefficient were a variable and not a constant, then we'd have to do something else, but that's it. And here we've got 2 cosine of x, and it's mixed with a polynomial expression. No problem. We've got the power rule for that. Y prime is 15 x to the 4, subtract 1, derivative of 2 cosine of x. So we're going to get 2 multiplied by the derivative of cosine, and the derivative of cosine is negative sine. So really this is going to become negative 2 sine of x. And so you'll start to get that idea that anytime I take the derivative of cosine, I'm going to just change the sign of what's out in front. It's going to become opposite because of that opposite rule right there. And here we go. We've got a cosine, but it's mixed in with this. Just if you can do this mentally, that's okay, but you still might like to take a step and rewrite this in exponential form, power rule format. That's x to the 1/3, and since it's in the denominator, that's really x to the negative 1/3. And I haven't done any differentiation yet. I'm just rewriting it so now it's ready to go. So the derivative f prime of x equals negative 1/3 times 4/5 is negative 4/15. X to the, subtract 1, negative 1/3 minus 1 is negative 4/3. And now the derivative of negative 6 cosine of x, it's going to be negative 6 times the derivative of cosine, which is negative sine. So again, we get that sine flipping to positive 6 sine of x. And in my book, I don't like this as a final answer because of that negative exponent. So if you can switch it all in one step, again, that's okay. Just don't make a silly mistake. Move this to the denominator, so negative 4/15 x to the positive 4/3 plus 6 sine of x. You want to make it radical form? Be my guest. You want to rationalize the denominator? Be my guest. But don't leave the negative exponent. Okay. Now that you know a couple new rules, and this kind of happens in calc as you go throughout the year, you learn a couple new rules, you learn more and more ways to handle derivatives, and then you approach some of the same questions now of applying them. So one classic question is writing the equation of a tangent line at a specific point. So I want the line tangent to this function at 2 pi over 3. So what do we need? We need two things, point and slope. I don't have the y-coordinate for the point, so I got to get that at some point. So h of 2 pi over 3, right? I'm going to plug this into the function, use good notation, and we'll have 6 times the cosine of 2 pi over 3, and then minus 5. Now cosine of 2 pi over 3, I think we can do that in our head. That's quadrant 2, so it's negative, and the cosine of any pi over 3 is going to be that 1/2 ratio, so negative 1/2. Negative 1/2 times 6, negative 3. Negative 3 minus 5 is negative 8. So our point is 2 pi over 3, comma, negative 8. Now let's get that slope. That's what the derivative is all about, of course. So h prime of x is equal to, what's the derivative of 6 cosine? Negative 6 sine of x. Derivative of negative 5? Gone. It's a constant, right? Derivative of any constant is 0. And now let's get the slope at this specific point. So we plug in that x value. So h prime of 2 pi over 3 gives you negative 6 times the sine of 2 pi over 3. Sine of 2 pi over 3 is quadrant 2, where sine is positive, and the sine of any pi over 3 is that root 3 over 2 ratio. So positive root 3 over 2 multiplied by negative 6 is going to give you negative 3 root 3. There's your slope. There's your point. Point slope form. Y plus 8 equals negative 3 root 3, the slope, times x minus 2 pi over 3. And this should definitely convince you of why point slope form is nice. You don't want to be finding the b value, the y-intercept, when you got slopes of 3 root 3 and 2 pi over 3 as your x-coordinate. Just put them in point slope and move on, right? Okay. So, last question here, another classic. Find any points where this graph has a horizontal tangent line. Sine of x plus x. So the midline is like a variable. It would look kind of like this. If you were looking, it would look like a sinusoidal, but it would actually kind of have a slope, like a linear slope. It's got a linear midline. Kind of cool. But how do we approach this? It doesn't matter what function they give us, and they're going to ask this over and over again. When does it have a horizontal tangent line? That is really saying, when is the slope 0? Or in other words, when is the derivative, or y prime, equal to 0, right? Because the derivative gives you the slope. So let's find that derivative. Y is sine x plus x, so y prime is, derivative of sine is cosine, derivative of x is 1. And now we want to solve for x values in this interval where this equals 0. So we set our derivative equal to 0 and solve. Sometimes that's factoring, sometimes it's trig. Here we go, we get to brush up on our unit circle. When does cosine equal -1? Hopefully it doesn't take you too long to come up with. That is at x equals pi only within this interval. So are we done? No, because they said points. So they're looking for the y coordinate as well. So now I know the x value. How do I get the y value? You plug pi in to the original function. So y of pi is sine of pi plus pi. What's the sine of pi? 0. 0 plus pi? Pi. Y of pi equals pi. So the point is pi pi. There we go. And on that note, I will see you later. So pi pi, kids. Let me know if you have any questions. Adios.